Sorry about that. I think I got kicked out. All right, so I was sharing my screen when it all went down. Okay. Hopefully, I had to get out of a lot of stuff, so. If this doesn't work, we'll have an alternate. There's no problem. I just want to know whether it's working or not. Because it looks like Wiley. There we go. For some reason, I keep going in and out today. All right, so I was going to show you that I had the lecture, but not this one. I have it. Maybe I don't have it. I don't have it. I'm going to convert it. I thought I had created it already, but maybe not. It was Friday, whenever Friday it was. Let's see. What day was Friday? Well, the 1st. Yeah, I don't see it here. Okay, so we're going to upload. Let me select. It is let's see, documents, Zoom. And 04. No, that's what we've been trying to do, but this is the one we need. Okay. That's what's in there. I don't even know what we called. I don't remember. Polarity and internet. Yeah, I think so. And intermolecular forces. Oh, and the properties of water. Oh, okay. That's what it was. Okay. Okay. It's uploading right now. So if you can hear me, good. All right. So we were doing an activity. Let me see. I still haven't gotten to Canvas because it wouldn't let me in. It still won't. Okay. Yeah, lucky for you, I saved it. I think. Let me check. Recent. No, I like that. That's per lab. Yeah, see, there it is. Okay, so this is the activity we were supposed to have done not yesterday, but Friday. And this is you can download it. And this is the thing that we were talking about was polarity. And it says all groups in the central atom have to be identical. And it has no lone pairs. So these two things are the two things that are important for polarity. Now, what you're going to do is you determine the Lewis structure, the electron group geometry, molecular geometry, blah, 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 all that stuff, which is right here. Now, unfortunately, the Lewis structures are gone now because, I wrote them and everything else has been answered. Now, as far as London dispersion and all of that, the PowerPoint is called intermolecular forces. And it's the second one, not the first one. And then on top of that, I went ahead and I did the properties of water. And that was all that's in that lecture, just so you know. So right here, if it would let me in. There you go. It's letting me in. Good. Finally. All right. It's letting me into Canvas. So that's good. All right. We can look and see what's next. I was trying to show you, but I couldn't show you because I couldn't. All right. So you have an assignment coming from that lecture that none of you was here to see. But I did talk about it, and it is in that recording. And this is it right here, VSEPR and IMF. Okay, right here. It's exactly what we did on the, it's not showing, let me download it. Yeah, it's exactly what we did here, right? Except there's different compounds. That's the only difference. Okay, so for some reason, this one doesn't want to come out. Okay. Yep. Looks like we keep going in and out today, like we did a few times before. Okay, so I'm going to open this file. You're probably not share mode anymore. Okay, there we go. All right, so the sharing, there it is. Okay, so this is the one that you're supposed to do. Okay, so you're supposed to draw. You notice it says for each of the following molecules, draw the Lewis structure. If there are any resonance, draw them too. Indicate the molecular shape and the bond angle. Indicate the polarity. And identify the major intermolecular force. Okay, so let's say we were doing carbon tetrafluoride. Okay, so this is what it should look like. And I'm just going to do one because you guys weren't here before. And you need to be watching that video at some point. Okay, so carbon tetrafluoride, you would have to do the math. So first thing I'm going to do is do that. I'm going to put in a text box. Okay, and we have one carbon in group 4, right? Plus we have 3, 4, because it's tetrafluoride, right? Times group 7, because fluorine is in group 7. That is equal to 21, no, 28 and 4 is 32, right? Okay, when you draw this, one of the things I showed you was to start drawing the crude sketch, which is without dots as of yet. Oh, let me make it a little bit smaller. Let me clear that. Oops, I didn't mean to clear that. undo. I need to clear this, but not that. Okay, there we go. This is too big. Hopefully I can make it smaller so you can see it. Okay, so carbon tetrafluoride. Right, so that's your crude sketch. From the crude sketch, you come back and you do a subtraction, 32 minus. Okay, so there are 4 bonds. So 4, and each one takes 2, right? So that gives me 24 again, right? Because we're needing take 32 minus 8. Okay, so that gives me 24. 24 is how many we need, because we need, oh, come on, give me that. 6 on each one of the fluorine atoms. Okay, and that, okay, so that would be your Lewis structure. The next thing to do, okay, we did the math to get to the Lewis structure. But the next thing to do would be the molecular shape and the bond angle. Well, since it is an AB4, and that's in your, it's in your sheets that we were looking at, the VSEPR lab. This is a tetrahedral shape. And it is a non-polar molecule because it is symmetrical, so it's non-polar. And the bond angle is going to be 109.5. Okay, now there are no resonance structures, so you can write that down or just leave it alone. We did everything it says except one thing. We haven't done the major intermolecular force. Since it is a non-polar molecule, it will not exhibit dipole-dipole. It's not charged, so it cannot have an ion dipole. It definitely doesn't have hydrogen bonding, because for hydrogen bonding, you have to both be polar and have hydrogen bonded to either fluorine, oxygen, or nitrogen. And none of those are here. So the only intermolecular force that would come on would be London dispersion. And you can just call it LDF if you want. So London dispersion force. That's what, in that other thing that we were looking at, let me have my mouse back. In that other thing that we were looking at, the VSEPR, I think I accidentally closed it, darn it. I hate when I do that. Let me see if I can find it. Yeah, I did close it. Shoot. Okay, yeah, I closed it. I did, but I'll find it. And that's the best part, but I want the one with the answers. So it's a quick access. It's documenting VSEPR. I just need VSEPR tab. There we go. And I want the one with answers. There it is. But it needs to say answers. No. I don't see it. I just opened it. Maybe it's in here. There it is. Answers. All right. Okay. Once again. Here we go. They have the answers all in here, you see. All right. So the ones that are polar and this is written right here, and I highlighted it. You have no lone pair electrons, and this one didn't. And all of the atoms are the same, so that are attached to the central atom. They're all fluorines. So that would have made it non-polar. Now, as far as the intermolecular forces, one thing I can tell you is when you have a London dispersion force, it is in every molecule. It doesn't matter whether it's polar, non-polar, ion, not ion, they're all London dispersion. The next thing that you're going to have, if it's polar, it's a dipole-dipole. If it's charged or polar, it can either induce an ion dipole because it's charged or because it's polar. So it has an ion dipole also. And it only has hydrogen bonding, like I said, if it is bonded to hydrogen, if it's a hydrogen bonded to an oxygen, like right here. See? So none of those, even though they all have oxygens, none of them could have hydrogen bonding because not one of them is bonded to oxygen. So it's oxygen, fluorine, or nitrogen. But it has to be hydrogen, right? So hydrogen bonded to it. Then you have, okay, so let me erase that. And erase this. Okay, so let's go and see the next thing. Okay, the other thing is if you're charged, of course, you're going to be able to induce an ion dipole. So this one would have ion dipole. So with this, this, and this, but not this. But it could induce an ion dipole because it is polar. So that's another thing. Even if it's non-polar, it still can induce an ion dipole. But if it is polar, it can also do so. So just remember these few pointers here. And the last thing is, hydrogen bonding. And like I said, that one had hydrogen bonding. Only ammonia here would have it. See, there it is, hydrogen bonding, and H3O plus, or the hydronium ion would also have it, but nobody else. And now this last guy right here, this CL3, that one, even though everything points to the non-polar, you have one atom that is bonded to the central atom that is not the same as the others. So even though you have, a tetrahedral structure, which indicates you have no lone pairs, even though you have all of that, this guy right here makes it all become polar. Because if we were to do the dipoles for hydrogen, hydrogen is less polar than carbon, so the dipole would go that way. Carbon is less polar than chlorine, so the dipole would go that way. Dipole would go here, and the dipole would go here. These two will cancel, but these two will add. So you end up with a net dipole going down. You see? So that is what you're looking for. You're looking for a polarity that is going to add up, not subtract. This had been CCl4, carbon tetrachloride, then it would have not had this dipole. It would have all canceled. And that's what you're looking at, okay? So let's erase this. And that's all there is for this part. Now, as far as that goes, that's your homework, but let's clear all of this because I need to go elsewhere. And let's start on something else. Let's see, mouse back. All right, so we have, our next thing is to learn to, let me go back to it. So okay, so let's see here. I'm checking to see if it's open or not. If it's not, it's going to get open today. It's not. Okay, so it's going to open today. And it's going to close at the end of the month. But remember, let's just say April 30th. Yeah. Let's make it the end of this month. But it'll actually be due on the 11th. Okay. Just so that you know that part. Oh, yeah, it's already done. Okay. All right, there you go. All right, so let's save it and go next module. After this module's over, which it is, this was all about molecular structure for covalent mainly, and also how the dipoles go. Remember, the dipole moment has to do with electronegativity. And we learned that electronegativity goes, oh, hold on, I'm trying to get the tools so I can show you how it goes. Okay. There we go, we're sharing again. Okay, so it goes from, in case you remember, I don't know if you remember, but it goes from left to right, right? Fluorine is the most electronegative, and then bottom to top. That's how it increases. So remember, if anything is over here, like carbon, and you have fluorine with it, the dipole is going to go towards fluorine. But let's say you have hydrogen over here, the dipole is going to go towards hydrogen. Okay, so that's what you want to know. Okay, all right, let's go to the next section, next module, which we're almost done. One of the things I saw in there is that you need to learn how to do molar mass, which molar mass is super easy. We will do that next. There it is right there. You see it? Okay, so molar mass, it actually shouldn't even be on there. That's why I think it's a weird place for it, but that's all right. Molar mass basically is taking the name or the formula of a compound. Let's say you had, let me pick a big one so that you'll, sorry, I have to grab my stuff, which is all the way in the back. My office, I have to stretch. Okay, there we go. All right, so let's say we have a nickel. Where are you? I'm just going to give you one, but I thought, well, no, let's use one that we've used before. So I'm looking for that one sheet, that 50 ways to name your compound, and I want to get one of those hydrates. That way it'll all become very clear. You just gotta find it. So keep all of my stuff in one place. And that might be too much. I think I have a lot of periodic tables in there too, because people always leave their periodic tables. Here we go. All right, so let's say we had nickel 2 sulfate hexahydrate. So nickel 2 sulfate hexahydrate. Okay, so for this kind of thing, okay, what we need to do is we need to look at all of our atoms that are in here and know exactly how many there are and use our periodic table for each mass. So in this case, it would be 1 nickel times And I'm just putting 1 so that you know there's 1. 1 nickel times 5869 plus, you have 1 sulfur again at 32.07 plus, you have 4, sorry, somebody's at my door, 4 oxygens at 16 plus, you have 6 times 2, right? So 6 right here times 2 here. So you have 12. You have 12 hydrogens times 1 plus 6 times 1 is 6 oxygens again. Okay, so when you add all of this, you get what is known as the molar mass. So if you do it in the calculator, like I did, but don't even worry about the ones, but I put the ones so that you know that that was 1. So it's 58.69 plus 32.07 plus 4 times 16, right? Plus 12 times 1.01. I put 1 as 1.01. Oops, 1.01. There we go. 12 times 1.01 plus, again, 6 times 16. All right, the whole entire molar mass of this compound is 262.88 grams per mole, hence the name molar mass, because it's per mole. And there you go. So let's do another one that's a little like these. All right, let's let you guys do one and you tell me what you get on yours. All right, let me do not an easy one. Let's do this one. I'm not doing another hydrate, but I am gonna do a different one. Okay, so chromic acid. Let's do chromic acid. Let's clear all of that. And the one that you're doing is H2Cr04. Okay, so you tell me what the mass of it is. When you're done, you can chat it through. Okay. Let me know when you're ready. Okay. Somebody's got it. Okay. All right. Well, I guess you'll watch the recording. Anybody has it yet? All right, for H2C2, HC2H3O2. Okay, somebody's got it. All right. Who's got the other one? This one yet? Do you have the Molar Mass for it yet? Remember, the masses come from the periodic table. That's why I said you have to look at your periodic table. So, okay. So to do this one, right, you have 2 hydrogens, and each one weighs 1.01 grams per mole. Plus, you have 1 chromium at 52.00 grams. Plus, you have 4 times 16.00 for the oxygens. That gave me 118.02 grams. Okay, but anyway, I was showing you how to do it, and then the thing cut out, but it ended up being 118.02. If that's what you got it right. All right, let me see, where am I? Sharing screen again. And when we're doing this annotation thing, the drawing, it was 118.02 grams per mole. So that's what molar mass looks like, okay? Basically, you're just adding. All right, let's do this one, and that'll be the last one. Oh, no, clear. There's no 2. HC2, H3O2. Oh, I want the skinny. Yeah, there we go. H3O2. So it's all of that, just that my H is kind of far out, but let me put it closer. There, that's the mass that we're looking for. Try doing that one. See what you get. I got 60.06 grams per mole. All right. Let's clear that. All right, for that one, I had, let's see, HC2, H3O2. All right, so I just took both of those together and I said 4 hydrogens, right, times 1.01 plus 2 carbons times 12.01. Remember, this is all from the periodic table, times plus 2 times 16 for the oxygen, gave me a total of 60.06 grams per mole. Okay, that's the one. And then we have one big one. And I know I said that's the last one. I mean, that's the one before last, because I also wanted you to do this big one, which is magnesium sulfate non-hydrate. Magnesium sulfate non-hydrate. Okay. It's always good to have something in parentheses when we're trying to do these. That's what I was trying to look for one. And I couldn't find. Oh, yeah, there's one. Ammonium carbonate. So ammonium carbonate, if you have parentheses, right? That's multiplying, this number is multiplying that number, which is a 1, and the 4 makes it an 8. So then you would have 1 nitrogen at 14.01 plus 4 hydrogens at 1.01 plus, not 4, sorry, 8 hydrogens. Sorry about that, 4 times 2 is 8. Anyway, yeah, that's it. It is the last one I'm doing, and we'll be done for today. I'm gonna do it on the board so you guys can see it. I'm gonna share my whiteboard this time. All right. So for this next one we're doing is ammonium nitrate. No, not nitrate, carbonate, sorry. Carbonate, not nitrate. Nitrate wouldn't have to like that. Carbonate. Okay, so we need 2, right? Because this is multiplying both of those times 1.01 plus, going to have 8 times a 1.01. Oh, sorry, 12.01. Clear. I was doing the nitrogen, and I was thinking of the carbon, of the oxygen coming next. So that's why I messed it up. That's 14.01. Okay. Plus, you have 1 carbon at 12.01. See, I was already thinking about that. Plus 3 times 16. And that's going to give you the molar mass of ammonium carbonate. All right, so I get 2 times 14.01 plus 8 times 1.01 plus 12.01, because that's the carbon, plus 3 times 16.00. That gives me 96.11 grams per mole. All right, so when you have parentheses, remember you're multiplying this number times that number, which happens to be a 1, and that number, which is 4. So it makes it 2 and 8. All right, next one. We had magnesium sulfate monohydrate. Okay, so magnesium is 24.31. We have 1 of those. We have 1 sulfur at 32.07. Plus we have 4 times 16 for the oxygens. And then we have 18 hydrogens, times 1.0. Let me clear that. Okay, there we go. Times 1.01 plus 9 oxygens. 9. I keep doing that. Hold on. 9 times 16 again. All right. Now, that would give us a big total. So 24.31 plus 32.07 plus 4 times 16 in parentheses, just like I wrote it, plus 18 times 1.01 plus, last one is 9 times 16.00. That gives me a total of 282.5 56 in the units of rams per mole. All right, and that concludes it. That is all we have for today. And I will be posting this recording shortly. Bye-bye.